Welcome back to Easy Gates, Gate 22 Easy Solutions. One problem from digital electronics. Okay, next one. This is another 2 marks in multiple select questions. Hope you can understand the problem statement. What is given as a combination logic design function? It didn't say we said a function is realized. Okay, that is having two inputs A and B, and the function realized is A plus B bar. Okay, I hope he used A and B. Maybe instead of A and B, X and Y also. So the function realized is the one input comes as it is odd with another inputs complement. Okay, so here he also said in the problem statement the plus operator says it is OR operator. Okay, so it's a logical OR, it's not summing. Okay, fine, because sometimes we may perceive it's a arithmetic operator, but it is a logical operator. It's a logical OR, he said. Okay, so it's a stress on that. It's logical OR only. A or B bar, that's what it means. So using this logic function, he has given 4 options. Okay, it's a multiple select problem. So we have to choose what are all the right answers. So using the above logic function, he says NAND logic can be implemented, OR logic can be implemented, NOR can be implemented, then AND logic also can be implemented. That means what? He's asking simply whether the given function is universal or not. That means A plus B bar is universal or not means if you know the answer, already such a problem happened in the ECE gate paper. Okay, but in that problem, he has given 3 gates actually. Okay, but 2 gates are not universal. 1 is universal, that gate having such a function. If any gate has been practiced properly the old gate problems, and that will strike to the strike immediately once you see this, then you have to prove yourself that it is something relevant to that, but you have to build, because you can't simply do copy paste of, so there I have given the answer as universal, here also I have to give the answer as universal, so I'll go for clicking all the options. Yes, you have to prove yourself once. Okay, is it universal or not? For that, you take some logic function which can be implemented by the given function. Say for example, I have a logic gate. There is a gate, let me say. That gate is sensing 2 inputs, A, B, and producing as per the given data, it's A or B. Yes, that's a gate producing. So when it actually, it didn't say we can use sufficient number of them. By default, whether we can implement it or not. When you have a logic combination logic function, by using same logic function, n number of them, you can implement a function. Say for example, NAND. By using NAND logic gate, you can implement any function. By using sufficient numbers of NAND gates only, that's what it means. Similarly, by using sufficient number of NOR logic gates, you can implement any logic function. It can be SOP or POS. But we have a rigid thing, NAND, SOP, NOR, POS. Okay, so NAND and NOR, we call them as universal. So similar to that only, instead of giving NAND function or NOR function, he has given something new, calling it as A plus B bar. Okay, so then is indirectly asking whether it is universal or not. You have to feel it. Now let me take, so this is the gate. So this gate is producing A plus B bar. Can I implement NAND from this? Can I implement NAND logic from this? So what is NAND logic function? We know already. Okay, NAND means yes. This is my NAND. I have A, I have B. Result is going to be A dot B whole bar. A dot B whole bar will be the NAND realization. That means output of your NAND. And this can be called as F, this can be called as F. And here F is equal to A or B bar, but here F is equal to what? A dot B whole bar. But we need to have that common operator between them, means you can expand by using De Morgan's. You can make A bar or B bar. Yes. Now, in the place of B, you can give B. But in the place of A, if you give A bar for this, say for example, I have this gate, gate 1, let me take. For this gate 1, shortly G1, I'm giving, this is A and this is for example B. What the output it will produce? It will produce A plus B bar. In the place of A, let me connect X. In the place of X bar, let me connect. In the place of B, let me connect Y. Tell me what it will produce now. the output functionality. Now what it will produce? So it is going to copy the A as it is. That means X bar will come as it is. Then R. And in the place of B, what I have is Y. So the result is going to be Y bar. That means that it can implement X dot Y whole bar indirectly. It is implementing X bar R Y bar, which is nothing but X dot Y whole bar, which is the essential NAND logic function. Means what? NAND can be implemented by using how many? By using how many? That is not the question here. Using sufficient number of them, that's how you need to pursue the problem. It is worth of 2 marks. You need to check for every logic function given in the option. So NAND can be implemented, but problem is I have X bar. How to implement this X bar? You have to think how to implement this X bar. So if I implement this X bar, it is possible to generate X dot Y whole bar. Then this is a NAND function. Then how to implement X bar? So you can think smartly. So take another gate, call it as gate 2. So now tell me how to get X bar. The result has to be X bar. How we can produce X bar? So let me say this is A and this is B. The result is going to be its second gate. Okay, result is going to be still A plus B bar. But I'm looking for X bar here. I'm looking for only X bar. So that means what? Compare. A can be 0. Connect A to 0 and B to what? X. Done. So this is gate 1. This is gate 2. By using 2 identical gates, gate 1, it's possible to implement NAND function. So that means the question is whether we can implement NAND logic function by using the given logic function F is equal to A plus B bar or not, means yes, we can implement. If NAND is implementable, already the gate 2 is implementing only what? This gate 2 is implementing not. It's an inverter. And thing is that if any logic function first is capable of implementing not, then we have to prove it is capable of implementing and. Then capable of proving it is what? We should prove it is capable of producing what? R. If you know how to, if you know it is realizing and or an inverter means by using AOI gates, any logic function can be implemented. So you can go for, so not is capable, not by using the given function, you can implement a not. Then NAND is possible means, so you have implemented already NAND. So just complement your NAND. NAND output is implemented already by using 2 gates, given functionality 2 gates. So X dot Y is already available, whole bar is available. Then feed it to one more gate 1, then you will produce. So connect this to 0. This is A, this is B, and the gate is blind. It is going to make A plus B bar. And A you made 0, B already connected to what? X dot Y whole bar. Therefore, the result is going to be X dot Y. This is realizing what? And function. This is realizing and function. So you proved it is implementing and it is implementing what? A and it is implementing inverter, it is implementing and you have to prove only it is also producing what? R logic function. Then it is universal. Then you can click all the options because all are logic functions, proper logic functions. It can be implemented by using this universal logic function given as A plus B bar. Okay. Yes, now I need to prove myself again it is possible to implement R logic as well. What is R logic? R logic means the function has to be A or B. Let me say otherwise, let me take X and Y. I don't want to disturb the gate inputs. Let me take it as X and this is Y. I want to implement this. But my gate knows only one theory. If its input is A, another input is B, it is going to produce only what? A or B bar. I want to match A or B bar to X or Y. So then tell me what is the input to A, what is the input to B. I can feed X to A. I can feed what? Y bar to B. Okay. So that means what? X equal to A, you can say Y is equal to B bar. So, but B is the input, then B should be equal to what? From this Y bar. So then how to get Y bar? Yes, you know already how to implement a not. Okay, then keep your A to 0 and B to what? Y. Then the same gate will produce the output as what? B bar. That is going to be Y bar. Feed it. Yes, R is also implemented. So that means it is possible to implement AOI means Yes, the given function is universal. Using sufficient number of this logic function, we can implement any logic function. That means answer is you can implement any proper logic function. Yes, NAND can be implemented, OR can be implemented, it's proved. NOR I didn't prove, you know how to complement your NOR. Okay, yes, NOR can be implemented and can be implemented. I have proved already NAND, I have proved, OR I have proved, and I have proved. So then once you know OR complemented, the result is going to be NOR. So the correct answer is all the options are correct. So by using the given logic function, you can implement NAND, NOR, and OR, even inverter. That is possible, but is not giving that hint. Usually when you want to prove something universal, you have to begin with implementing inverter using that function. So the moment it is implementing inverter, then you have to try for AND and OR. Then if it is succeeding in this attempt, it's a universal logic function. So that's a wonderful problem using combination logic. Okay, so universal logic function given, with that you can implement any logic function. So all the options are correct. All can be implemented using the given combination logic function or combination logic design. Okay, that's a very interesting problem from digital. So do subscribe our channel. We'll update you with one more problem soon.